Hi students, in this lecture we are going to learn conductors in electrostatic field. Let us see what is it. Let us consider a conductor. It can be any shape. So we are placing now this conductor in electric field. There is some electric field in this region. Now in that electrostatic field, we are placing a conductor. So we are knowing that conductor is having large number of free electrons, right? So once we are placing a conductor in electrostatic field, these electrons will distribute, or you can say redistribute in such a way that inside the conductor, electric field becomes zero. Let us take this as E dash, electric field outside the conductor, right? So now what we are saying is that electrons in the conductor, they redistribute in such a way that electric field inside the conductor becomes zero. Okay. Now see carefully. If we take Gauss law, consider a Gaussian surface. You can see here I am taking the Gaussian surface just inside conductor. Just inside conductor. This is now Gaussian surface. I am showing with the blue lines. Just inside. So we are taking a Gaussian surface just inside. From Gauss law, net flux equal to net charge inside upon epsilon naught, right? And here electric field equal to zero. Electric field zero means flux is zero. I am repeating, no electric field, no electric flux. That implies net charge inside the conductor equal to zero. What is it? Net charge inside the conductor is zero. That means now here number of electrons and number of protons both are equal. That's why net charge equal to zero, right? Okay. Now electric field is zero means, if you remember, we have learned earlier E bar equal to minus del bar into V. Reading this as electric field intensity is equal to negative of potential gradient, right? So since the field is zero, its meaning is potential is a constant. Okay. So this is nothing but derivative of the potential, right? So E bar zero means derivative of potential is zero. Means here potential is constant. So next important point in this, it is potential. That implies potential inside is a constant. Okay. So this is a equipotential region. What is it? This is a equipotential region. And if you take surface, it is equipotential surface. Okay. And see carefully. Again from same relation, E bar equal to minus del bar into V. So here we are saying that along the field direction, potential decreases, and normal to field direction, potential does not change. Now take this point here. So here we are saying that on the surface also, On the surface also potential is a constant. That says that from that what we can say is field must be normal at each and every point. Field must be normal at each and every point. See why it is normal. When field is normal at each and every point on surface, if we are moving along surface, if we are moving along the surface, potential does not change because along the field potential decreases. Normal to field potential does not change. So here it is now equipotential surface. That is possible if net field or it is a field is normal at each and every point. Okay. So here conclusion is that inside the conductor field is zero. Since the field is zero, potential is a constant. So this is now equipotential region and surface. It is an equipotential surface. So since it is equipotential, field will be normal at each and every point. So we have earlier learned that equipotential surfaces at each and every point on the equipotential surface, field will be zero. So take the same point here also. It is normal at each and every point on the surface. Right? Okay. Now let us consider. Suppose from this conductor, from this conductor, remove some part of the volume. Remove some part of the volume. That means we are going to get a cavity. What is it? This is now cavity. So we have removed some part of the volume from the conductor. So we are having a cavity. Now inside cavity also field will be zero because before removing this field was zero, right? After removing also field remains the same. That means again E value how much? Zero. So inside cavity electric field will be zero if there are no charges in the cavity. I am repeating, inside the cavity electric field will be zero if there are no charges inside the cavity. Right? Now see carefully. What happens if we are placing charge inside cavity? See here. This is a conductor. Inside that conductor, we are taking a cavity. We are taking a cavity. This yellow one indicating cavity. Let us consider a charge is placed inside cavity. That is now Q. Suppose it is now plus Q. A positive charge is placed inside cavity. Okay. Now see what happens. Because of this positive charge, electric field is present in the cavity. And we can see one more point. We have learned that electric field lines due to a positive charge, will be away from the charge. It remains radially outwards, right? Electric field start from positive charge and end on negative charge. Field lines, they have to end on the inner face of cavity. So where they end? They end on inner face of the cavity. Its meaning is that inner face of the cavity becomes now negatively charged. I am repeating. Electric field lines start from positive charge and end on negative charge. So these field lines will terminate on inner face of the cavity. Therefore, inner face of the cavity becomes negatively charged. Okay. And remember, in this region, this is now a conducting substance. In conducting substance, electric field is zero. That means in this region, we cannot expect electric field lines. I am repeating, in this region, we cannot expect electric field lines. Okay, that's why they terminate only on inner face of cavity. So its meaning is that this positive charge is going to induce negative charge on inner face of cavity. This positive charge inducing negative charge on inner face of cavity, are saying same thing in terms of field lines. Field lines start from positive charge, end on negative charge. Means these field lines terminate on inner face of cavity. That means the inner face of the cavity becomes negatively charged. And once it becomes negatively charged, positive charge will be on the outer face of the conductor. So this becomes now plus Q. Remember, all field lines starting from plus Q, they terminate on inner face of cavity. All field lines coming from positive charge, they terminate on inner face of cavity. That means charge on inner face of cavity equal to minus Q. So its meaning is plus Q is inducing minus Q on the inner face of the cavity. Then remaining will become here plus Q on outer surface of the conductor. Okay. So here field is remains zero in the conductor. But now field in the cavity is not zero because charge is present. Okay. And here we can give one more conclusion. One more conclusion. See carefully. Let us consider Gaussian surface just outside cavity. Just outside. There's a green lines indicating Gaussian surface just outside cavity. Okay. Since we have taken Gaussian surface in the conductor, electric field is zero, that means flux zero. What is that? Flux zero. Flux zero means that implies net charge inside the cavity should be zero. Okay. That means from this also we can say that plus Q inducing minus Q charge on inner face of cavity. Otherwise, we are saying like all field lines terminate on inner face of cavity. By using that logic also we can say it is minus Q. Okay. So when this is a minus Q, outer will become plus Q. So cavity is now having no net charge. What is it? No net charge. So here conclusion is that if any excess charge is given to the conductor, if any excess charge is given to the conductor, that excess charge comes onto the surface. Means excess charge resides only on outer surface of the conductor. That's why having here plus Q. So we have given plus Q inside cavity and we got a plus Q on outer face. So what is the net inside means? It is zero. Okay, right. Let us see here some more points. Let us take a spherical conducting shell. Let us consider spherical conducting shell. Okay, it is a conductor. Let us take radius equal to r. Okay, assume there is no electric field in this space. Okay, now what we are doing is what we are doing is, okay, do one thing. Initially, no electric field in this space. Okay. So distribution of charges. What is it? Distribution of charge. I am giving charge Q to this one. Okay. A charge Q is given to a conducting spherical shell. What is it? Conducting spherical shell. Charge Q is given. Inside the shell, no charge. Therefore, inside the shell, there is no electric field. In fact, this is nothing but a cavity, right? So when you are taking a spherical shell, the inner one is nothing but a cavity. Inside the cavity, no charge, that's why no electric field. So now we have given charge Q. We have given charge Q. Now this charge distributes on the surface of the shell uniformly. I am repeating, this Q charge distributes on the surface of the shell uniformly so that inside the conductor field will be zero. Okay. Now what we are doing is we are placing a charge. Let us take like this. We are placing a charge. We are placing a charge. Suppose it is a capital Q at some distance r. At some distance r from center of the shell. Okay. Now see what happens. When this charge was not there, distribution of this charge on surface of the shell, it was uniform. Okay. But now what happens? Because of this charge, inside the cavity, field is not zero. Students, follow this point very carefully. Because of this capital Q, field inside cavity is not zero. But we are knowing that inside a conductor, field will be zero. That means now this small q on the surface of the shell redistributes. That means now distribution of charge on the surface of the conductor is not uniform. It is now redistributing in such a way that field inside cavity becomes zero. I am repeating. When this charge was not there, Q distributes uniformly on the surface of the shell. But when Q charge is placed here, Q charge is placed here, then this charge now redistributes so that inside the cavity, inside the cavity, field becomes zero. That means field due to this capital Q, field due to small q, total value is now zero inside. It is zero inside. Okay. Suppose a question is asked like, what is the field due to capital Q at the center of the shell? Then see what happens. At the center of the shell, because of capital Q, field will be, see, whenever you want to calculate a field, imagine a unit positive charge at that point. If I imagine unit positive charge here, if this is a positive, this will repel. Therefore, it will be K Q by R square. Direction is left side. Okay. Now, this Q distributes non-uniformly, or we can say redistributes in such a way that that charge produces a field inside the conductor which will cancel field due to capital Q. So at the center, because of this charge, field will be same value K Q by R K Q by R square. Direction will be right side. Now these two will balance. That means field due to Q plus field due to small q total equal to 0, 0 bar. Okay. So first case, charge was not there. Distribution of charge uniform. Now charge is present. Distribution of charge non-uniform. Ultimately, inside the shell, field is 0. Right? Okay. Let us take one more point here. See here what we can say. Right. Let us consider this is a conductor. Inside a conductor, there is a cavity. There is a cavity. Suppose having a charge Q inside. And there is one more charge, let us say Q1 outside. And there is some charge on surface of the conductor Q2. So there is a charge Q1 outside, charge Q2 on the surface of the conductor, and charge Q in the cavity. So here what we are saying is the resultant of electric field due to Q1 and Q2 will be 0 inside the cavity. Okay. The resultant of Q1 and Q2 will be 0 inside cavity. So inside cavity, field is only because of the inner charge. The effect of all outer charges. What I am saying? Effect of all outer charges, including the charges on the surface of the conductor, will be 0 inside the cavity. Okay. In the same way, what we can say is effect of this charge inside cavity in the outer region will be 0. For example, we are changing location of Q1. Still, inside the cavity field remains same. Suppose I'm changing location of Q inside cavity. Still, outside field remains same. Means field inside cavity does not depend on the charges which are outside the cavity or because of motion of the outer charges. In the same way, field outside the cavity does not depend on the charges due to due to inside the cavity. The charges inside cavity cannot influence electric field outside. Charges outside cannot influence field inside cavity. This is a forming a condition. It is called electrostatic shielding. What is it? Electrostatic shielding. So this is useful to protect some devices which are sensitive to electric fields. So keeping them inside a metal box. Because metal box in the sense it is now, it is a cavity inside conductor. Therefore, that device is not disturbed due to external electric fields. So this is what we call electrostatic shield. The reason is that field inside cavity is not influenced by the charges outside. In the same way, field outside is not influenced by the motion of charges in the cavity. Okay. Let us see once all these points. That's the first point. In electrostatic condition, electric field at every point within a conductor is 0. Any excess charge on a solid conductor resides entirely on its surface, right? This is what we have seen in case of a cavity, right? Next, any conductor in an electrostatic field is an equipotential region, and surface is equipotential surface, right? Next, electric field lines will be normal to the surface of the conductor at each and every point because it is an equipotential surface, right? The electric field in the cavity of a conductor will be zero if there are no charges in the cavity. Okay. Next, external charges, including the charges on the outer surface of the conductor, do not create any electric field in the cavity inside the conductor. And the last point, any arbitrary displacement of charges inside the cavity of a conductor does not produce any change in the field of the outer space. So these are the points what we have discussed till now.